Hi, everyone. My name is Ibrahim Sabek. I'm a postdoc at MIT CSAIL, and today I'm going to talk about LSched, a workload-aware learned query scheduler for analytical database systems. This is a joint work with my colleagues Tenzin, Ukyab, and Kraska. So the task of multi-query scheduling is to decide when and how the DBMS executes existing queries while minimizing overall latency. Assume that we have two queries, Q1 and Q2, that come to the system, and we want to execute them. So the first step will be to generate a physical query plan for each one of these queries. A plan will have a set of operators. For example, here we have Q1 as a simple join query that has 4 operators for scanning the 2 input relations, building and probing the hash table. Now, each one of these operators can be decomposed into a set of smaller operations that can run in parallel. We call them work orders. For example, in O1, each work order can just scan a small segment of the data. Some of these operators can be pipelined so that the work orders inside them can overlap the execution, and some of them cannot. For example, O3 and O4 cannot be pipelined because O4 can start probing until all the build tasks in O3 finish the execution. Once the operators and the work orders are ready to be executed, we first send them to the scheduler to find an execution order that will be followed by the query execution engine when we actually execute the queries. So why not just relying on the operating system to do the scheduling job? Operating system doesn't know exactly what happens inside the query execution engine. It's just a black box for it. On the other side, DBMS knows everything about the execution engine. And for example, you can imagine that the DBMS knows how many number of threads will be assigned to each operator, when the data will be cached, and so other information. In this case, the DBMS is more qualified to make scheduling decisions than the operating system. And that's why query scheduling becomes a core component in many database systems in the current days. However, finding an efficient multi-query scheduling policy is a pretty hard problem and requires considering a lot of operating system as well as DBMS specific factors. Examples of these factors are shown here. We need to consider, for example, the operator type, whether there are some pipelining opportunities or not, whether there is a workload specific behavior for these operators or not. In fact, having an optimal scheduling policy is very hard and is shown that it's NP complete. Existing scheduling approaches can be categorized into 3 main categories. In the first category, we have heuristic-based approaches. In this case, we have a fixed policy regardless of the workload that we have. It requires also manual tuning. In the second category, we still rely on the heuristic-based approaches, but the workload can be used to tune the parameters of the policies that we have. In the third category, we have end-to-end learned scheduling that can provide dynamic policy and can be changing according to the workload. In this case, we have the highest flexibility compared to the other 2 categories. However, state-of-the-art systems like Decima in this category considers only operating system factors and not a DBMS specific one. Here we try to address the research question that can we learn an end-to-end dynamic query scheduling policy that considers both operating system and DBMS specific factors? And the answer for this question is our system LSched, which provides end-to-end learned scheduling for operators inside the same query and across the different queries, while still considering the workload specific. But before getting into the details of LSched, I'm going to show an example on its efficiency. Here we have a query with 6 operators. Each operator is annotated with the number of work orders and the duration of each work order. To show the advantages of LSched, we assume that we have a support for pipelining in this query. And here we have 2 pipelines. We're going to show the scheduling decisions of 3 main policies, which are critical path, a heuristic approach that's well known for DBMS systems, Decima, which is a learned approach that doesn't consider pipelining, LSched, which is our proposed approach. Here we are going to assume that we have 5 execution threads to run all the work orders in each operator. And the x-axis will show how the time evolves during the query execution. And the yellow box here, we are going to show the scheduling decisions that are determined by each of these policies. We're going to start with the critical path. It picks the heaviest pipeline first, so it runs pipeline 1. In this case, we show here in this visualization any pipelining opportunity by overlapping voxels. Once pipeline 1 is finished, it runs pipeline 2, and the execution finished in 23 time units. Now we move to Decima. In this case, the learned approaches that we have doesn't consider any pipelining. However, it still provides efficient packing for the operators in order not to waste the execution resources. So it starts with O1, O4, then runs O2 and O5, then runs O3, and then O6. In this case, the total execution time will be 27. It's still a bit higher than critical path because it doesn't provide any pipeline. Now in LSched, it learns the proper degree of pipelining while still preserving the order of the operators that can avoid wasting the execution resources. In this case, we start with O1, O4 without any pipelining. Then we run a partial pipelining for O2 and O3. Then we run another partial pipelining for O5 and O6. In this case, the total execution time will be 20, which is much better than the other two processes. In this example, we just showed that considering only one specific DBMS factor like pipelining can greatly impact the execution time. And just imagine if we consider all the other competing factors in our learning policy, how much saving we will get. LSched has 4 main contributions. It provides the first reinforcement learning-based approach for query scheduling in databases. It comes with an efficient query encoding that captures the low-level representation of the execution environment in a scalable manner. It optimizes the scheduling policy in order to minimize both average and tail query latency. It also provides effective training phase and avoids training new scheduling policies for new workloads from scratch using transfer learning. As a summary for the results, LSched can improve the streaming and batching query workloads with at least 35 and 50% over existing state-of-the-art query schedulers. In this talk, I'm going to focus mainly on the first 2 contributions. The details of the third and the fourth contributions are in the paper, and you are welcome to check them. So the core idea here is to build a reinforcement learning agent that can learn the scheduling policy through trials and errors. It repeats the following process: provides a scheduling policy, evaluate its quality, and then update the internals of the scheduling agent till we converge to a good scheduling policy. Using trials and errors, the agent can learn what are the good and bad scheduling decisions. The agent takes 2 types of queries: the current queries that need to be scheduled and the executed queries. And the purpose of using the executed queries is to train the agent in the future. In order to have an efficient implementation for the reinforcement learning solution in LSched, we first need to find the equivalent representation for the problem in the Markov decision process context. In this case, we need to define state space, the action space, and the reward will be used for evaluating the actions taken. The state at any moment will be just the description of the execution environment and the current queries that need to be scheduled. Actions will be simply the assignment of the operators and work orders to the available execution threads at the moment. And for rewarding, we use the query latency. We assume here that we work in the single node in-memory database systems, and we just focus on scheduling the threads at the main execution resource for the scheduling. And of course, LSched is extensible to just support any scheduling for any other resources. LSched is basically following the native reinforcement learning framework. In this case, we have an environment as a DBMS engine. Once we have a user query at the runtime or at the training phase, it first generates the physical query plan for this query and use it as an initial set of features that will be used along with the current state of the execution environment as an input for the query encoder. And in this case, we generate a set of efficient embeddings that capture the current state of the environment and the execution execution engine. These embeddings will be further used by the scheduling predictor to schedule the set of work orders that needs to be executed to the available execution threads. Once there is an operator finished or a thread becomes available, query execution engine will send a signal to the predictor to fetch another set of work orders, and then the predictor will be scheduling a next wave of work orders. Once a query finished, it returns the output to the user. In parallel, also, it just use the executed work orders, reward them, and store them in the experience manager in order to just train the agent in the future. Now, for query encoding, we use tree convolution to represent the embeddings of each single query. In this case, a tree convolution captured the structure of the queries much better than other solutions like graph convolution and fully connected networks. This has been shown in previous work in learned query optimization. Standard tree convolution works as follows. Assume that we have a triangle filter like on the left side, and we have a query with initial vector of features at each operator. Now, the convolution happens as follows. We slide the triangle filter over the query operators in order, and the embedding at each operator will be calculated as the convolution output of the triangle nodes and the corresponding query nodes. However, standard tree convolution has two main limitations. First one, it doesn't support edge embeddings, which could be important for stuff like pipelining. Also, it assumes that the effect of the node on the other node's embeddings is equal regardless of the type of the workload that we have. So to avoid these two limitations, we provided a tree convolution network filter that can support both node and edge embeddings. And also we combine the graph attention network mechanism with the tree convolution to assign different importance to each of the node and edge embeddings. Now, once we generate the node and edge embeddings at the different nodes and edges in each query, we summarize these embeddings using a per query encoder to have one vector representation for each query. And after that, we also do a higher level summarization for this output query embeddings to have only one vector representation for all the current queries in the system. So at the end, we will have embeddings at 3 different levels. The embeddings here at these 3 different levels will be used by LSched to perform 3 scheduling decisions. The first one, to decide which operator to run now. The second one is how many operators needs to be pipelined starting from this operator. The third one will be how many threads to assign for running queries. In fact, each of these decisions will be an output of a separate neural network that estimates the probability needed to take this decision. Now we show a simple experimental evidence on LSched. Basically, we implemented LSched as a prototype inside QuickStep, which is an open source DBMS for analytical workloads. We evaluated LSched with 3 workloads, TBCH, SSB, and join order benchmark. We use average query duration as a main metric for evaluation. By query duration here, we mean the time that the query takes when it arrives to the system until it completes the execution. Here we show the results for the TBCH workload. We have 2 query modes, streaming and batching. In streaming, any query can come at any time instant. In batching, queries come in several batches. In each one of these query modes, we compared LSched, which is in dark blue here, with a bunch of baselines. And we report here on the y-axis the CDF of the average query duration. As you can see here, LSched provides at least 35 and 50% improvement over the closest baseline in both streaming and patching query workloads. LSched is more useful in the patching mode compared to the streaming one because in this case, the system faces a severe high load of the queries, and in this case, the resources become very limited. That's why having a careful tuning for the schedule decisions that we have makes a great impact. We repeated the same experiment, but now using job, which is having more challenging queries. And we found that LSched also provides better improvement ratio over the other baselines in both streaming and patching. This showed that LSched even works better in more challenging workloads. So in summary here, we just showed that learned query scheduling is an important problem. Heuristic-based approaches cannot capture everything in the workload. And we provided here the first learned query scheduler for in-memory database systems. We showed that the performance gain using LSched can reach 35 and 50% in both streaming and patching query workloads. For any questions, please email me on my email. And if you are interested in more recent work in our